Okay, we're going to develop our work on random variables now to take a look at continuous random variables. And just as a reminder, continuous variable is one that can take any value within a particular range. So we're going to be considering quantities such as time, temperature, height, any of the continuous variables that we may have met before. If we look at a particular example, let's consider this variable here, x, is defined as the number of hours that a particular battery will last. And let's suppose, for example, that the company in question claims that their batteries will last between 2 and 5 hours. Then we might represent the situation with a function such as this. So a continuous function to recognize the fact that any value of x between 2 and 5 can be attained. And of course, the function itself will define the likelihood of the battery lasting at particular times. Notice that before 2, the function is defined as 0, and after the 5, it's defined as 0. So we'll find that these functions are written like this. So I'll say between particular values, something interesting is happening, which will be defined by the function, and this will change from question to question. But elsewhere, outside of these limits, then the function is defined as 0. This means that then the probability of things happening after 5 and before 2 are going to be 0. Functions defined in this way that are used for probabilities are called probability density functions. So this is an example of a probability density function. Okay, and we need to be aware of some of the key properties of these probability density functions. The first thing to notice is that because we're going to be using them for probabilities, then probabilities are positive. So I'm not going to get PDFs that go below the axis. The next property is probably the most important, because if I'm going to use these as a measure of probability, then I need the total probabilities to be 1. So the area under this curve, under this function, the total area must be 1. Now this is the key property. If this is not true, I can't use the function as a probability density function. If I want to use it for probabilities, the total area must be 1. And of course, I can check this because I know that the area under curve is given by the integral. So because I've defined everything that I'm not interested in to be 0, I can set up the limits from infinity, from minus infinity. This will leave me only integrating the interesting bit, then the area must be 1. And I can use this to check whether things are probability density functions or not. This leads to the most useful property, which means then that the probabilities are given by areas. So if I'm asked, for example, the probability of the battery life being between 2 particular values, let's say we had A here and B here, I know that the probability that the battery life is between these 2 values is going to be given by the area. So I can say between B and A, integral of fx dx is going to give me the probability. So I'm in a situation where I'm going to be asked questions about probabilities, and they are going to correspond to areas underneath probability density functions. Use the properties of probability density functions to determine which of these could represent a PDF. Okay, let's take a look at an example of a common question and define a random variable x with this probability density function. So between 0 and 4, it's doing something interesting, and it's doing nothing everywhere else. So first thing that is likely to be useful is to consider a sketch. So straight away, I know that this thing is going to be quadratic between 0 and 4. If it's kx squared, then the x squared is 16, so that's going to be 16k there. I also know that from 4 onwards, the function is 0. So outside of this range, outside of this domain, sorry, the function is 0. So the function has 3 parts. It's 0, then it's interesting for a while, and then it's 0 again. So there's my sketch of this PDF. I may then be asked to go on and find what k is. And I can exploit the property here that in order for this to be a PDF, the area has to be 1. So I know that the total area between infinity and minus infinity of this function with respect to x must be 1. So relating that to my question here, I know that this part where it's 0, I can safely ignore. I just need this area in here to be 1. So the integral from 4 to 0 of kx squared with respect to x has to be 1. And I can solve this equation. In this case, fairly straightforward to do by hand. Let's go through. I can pull out the k. I can integrate the x squared, third x cubed. Between the limits of 4 and 0 is 1. So k, substitute 4 in, so that's 64 thirds minus substitute 0 in is nothing, is 1. So k times 64 over 3 is 1, so k must be 3 over 64. And that's the value that k must take in order for this area to be 1, and therefore for this to be a probability density function. Once I've got that, then I can answer particular questions. So the probability that this varies between 1 and 2, remember that corresponds to the area under the curve between 1 and 2. So I've got that problem to do. So the probability here is going to be integral between 2 and 1 of 3 over 64 x squared with respect to x, and it's a case of working this through. Let's pull out the 3 over 64 again, keep it out of the way, integrate the x squared, third x cubed, between 2 and 1. So this gives me 3 out of 64 into, what's this, x cubed, substitute 2 in, that's 8. 8 thirds minus, substitute the 1 in, 1 third. So I've got 7 thirds. So let's come up here, 3 out of 64 times 7 thirds. So the probability, 3's go, 7 out of 64. Of course, I can exploit my calculator to, in cases to find out k. I could get the calculator to do this integral for me here, and I could work out k. And of course, through here, I can easily get the calculator to do these as well. So if you've got calculator questions, there are big shortcuts that you can take in these particular techniques. Try this question, similar to the one we've just looked at. Try it with 2 ways. First of all, do it algebraically, but then take a few minutes to answer the same question with your calculator and identify efficient methods that you can use to get the answer from this directly from your calculator. That's what we'd expect you to do if this question comes up on paper 2. I'll finish this video with just a couple of things for you to think about. For example, for a continuous random variable x, what is the difference between me asking this question, what's the probability x is bigger than a particular number, and this question, what's the probability of x being bigger than or equal to a particular number? And of course, this then calls into the idea of what does it mean for a continuous random variable for the probability of it to equal a particular number. So put a little bit of thought to those questions, and we can perhaps discuss those in class.